4.5 Complex numbers. Complex numbers are numbers that can be expressed in the form a plus bi, a being the real part, bi being the imaginary part. I equals the square root of negative 1 if you do not know. The reason for this is because I equals the solution of x squared equals negative 1. And because nothing satisfies this, it is imaginary. Now since you know that I to the first power is square root of negative 1, what would I to the second power be? Well, obviously it's right here, but if you were to think about it, if you were to do negative 1, the square root of negative 1 squared, you just get negative 1 because they cancel out. Or if you're looking for I to the third power, it'd be negative 1 times I, which would be negative I. I to the fourth power would just be negative 1 times negative 1. And this pattern never stops. For example, if you're looking for a very high power, like an I to the very high power, you look at I to the 80th power. Now if you're not thinking about it, you'd be like, what is that? But since you know that 4 times 20 is 80, you can do I to the fourth power, and the outside do 20. Because that basically means 4 times 20, which is 80. So you don't even have to worry about this, since you know that this is what you're looking for. I to the fourth equals 1. So therefore you now know that I to the fourth power times I, well, plus it's multiplication here. So that'd be 80. So I to the 80th power would be 1. Now say if you have 75. You know that I to the 80th power now equals 1. And since you're minusing 4, you need 76. Because you minus 4, it's the same pattern of 4. Every 4 numbers repeats the same pattern of square root of negative 1, negative I, and 1. Because of this, you know that I, the 76th power, equals 1 because it is 4 less than 80. And because you know that this is 1, and that you're looking for 75, you can just subtract 1. Now if you were to go backwards from the pattern, 1 from 4, you get 3, and you know that's negative I. So that is why I, the 75th power, therefore equals negative I. So where are complex numbers in terms of all numbers? Well, basically, they are all numbers, because they require all reals and the pure imaginary numbers. And the reason for this is because you cannot have a complex number without having a real and an imaginary number. This being the real, this being imaginary, and same for this and this. Now obviously you know what a real number is, and you know what an imaginary number is. So this is how you would write it when you're taking the square root of a negative number. Because you cannot, you would substitute in I. But the reason for this is because since I equals the square root of negative 1, and you're looking for the square root of 15, if you multiply those together, you get the square root of negative 15 just like this. Now for one that comes out even, the square root of negative 16, since you know the square root of negative 1, you can just write I here. Now when you're looking for the square root of 16, you know that equals 4, so therefore you can just write 4i. Now it's a little hard to see, but graphing complex numbers. When you're graphing a complex number, it is basically like graphing any other number, but instead of x and y axis, you have the real plane and the imaginary plane. Now it still works just like any ordinary graph. The points are x, y, but instead of x, y, it's a, b. They're the same thing. A be going this way, and b going up and down. Now, this is basically your hypotenuse. This is where the point is. This is where it is from 0. This, theta, being the angle. This is the hypotenuse, which is r. And then you have your vertical and horizontal distance from 0, which equals r cosine theta, or r sine theta. Now, if you're going to graph just any ordinary complex number, or function I should say, like negative 3 plus 2i, since this is the a part and this is the b part, since it's just like this, x and y, you'd go to the left, negative 3, and up 2. That's your set coordinates. Now for this, 2 plus 4i, it's the same thing. You're going to go over 2 and up 4, and that's where you are. And for the same thing for this, you can go over 3, down 5, and there's your coordinates. Now multiplying and dividing complex numbers. We need to know a couple things. You need to know that z equals a plus bi. Z also is a complex number system. And the absolute value of z, which is also the absolute value of a plus bi, equals the square root of a squared plus b squared. And since you know that, and everything up here, complex number system 1 equals r1 times cosine theta plus sine theta. And this is 1, showing that this is for the first complex number system. And then 2, complex number system 2 is r2 times cosine theta 2 plus sine theta 2. Now r, as you see up here, this hypotenuse equals the square root of a squared plus b squared. Means that being the square root of a squared plus b squared, the square root of a squared plus b squared, you know that r equals the absolute value of z. Now, the formulas for multiplying and dividing complex numbers when doing it from a graph, it is complex, like so you have the complex system, number system 1 times complex number system 2 equals r1 times r2, and you take that solution and multiply by the solution of this whole thing because it's in brackets, and you're timesing it by the cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Now when dividing, so complex number system 1 over complex number system 2, you're doing r1 over r2 times the solution of cosine of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2. Now r2 cannot equal 0 because you cannot divide by 0. It's impossible. It's not real. Now some examples of this when you're not doing it from a graph right here. Here's some examples. We're going to look at this one first. It's 5 plus 3i times 2 minus 4i. Now there's two ways to do this. You can FOIL, or you can do it the way I'm going to show you. Basically, you can take this whole function, the number in parentheses, and times it by both of these numbers. It's the same thing as FOILing. So you're going to get 2 right here times 5 plus 3i plus negative 4i times 5 plus 3i. Now, after you do that, you're going to get 10, because 2 times 5, and then plus 6i, and the same thing here, just substituting for both of these. And then you're going to get minus 20i minus 12i squared. Now, you can see what I did here is, since you know I squared equals negative 1, you substitute it in. I have it written down right here. So, you're going to substitute it in and multiply, and you're going to get 10 minus 14i, because you're going to add like terms, plus 12. Then you're going to add like terms again, and you're going to get 22 minus 14i is your solution. Now for this example, you're going to have 3 minus 2i times 3 plus 3i. You're going to do the same thing. You're going to substitute this in for both of these, and you're going to get 3 times 3 minus 2i plus 3i times 3 minus 2i. And you're going to go through, you're going to substitute it in, and you're going to get 9 minus 6i plus 9i minus 6i squared. And because you know that I squared equals negative 1, you can just substitute that in, multiply, and you're going to get 9 plus 3i plus 6 after adding like terms, combine like terms again, and get 15 plus 3i. And that's how you multiply basic complex numbers. Now dividing is a little bit harder when you're going for just the straight complex numbers. basically what you're going to do is, because you know that this would be the numerator and this is the denominator, so that's how you're going to write it. But in order to actually divide, you're actually going to multiply by the complex conjugate to remove the imaginary part from the denominator. So what this is going to look like is that's the complex conjugate of the denominator. And it's going to be 4 plus 2i times 3 plus 3i over 3 minus 3i times 3 plus 3i. And after you're going to FOIL this. This is foiling this one. This isn't the other example I showed up there. This is foiling. So you're going to 4 times 3 is going to be 12. 4 times 3i is going to be 12i. 2i plus times 3 is going to be 6i. And then 2i times 3i is going to be 6i squared. Same for the denominator. 3 times 3, 9. You're going to do 3 times 3 here, and you get 9i. Negative 3i times 3 here, and you get negative 9i. And then negative 3i times 3i is going to get negative 9i squared. And because both of those equal negative 1, you can just substitute those in. Multiply, combine like terms, and you get 12 plus 18i minus 6 over 9 plus 9. And that's going to get you 6 plus 18i over 18. Now to get this in the a plus bi form, this is not a plus bi form. Okay? If you're trying to get the a plus bi form, you're going to have to do this. Because they're both over 18, you can separate them. Now this would get you your a plus bi. And then, because 18 over 18 is 1, you don't have to write that down. But 6 over 18 is 1/3, so you're going to get 1/3 plus I, and that's in a plus bi form. Now this other example, you do the same thing. 5 plus 4i divided by 3 plus 6i that's what it's going to look like. Numerator, denominator. You're going to multiply by the complex conjugate in order to remove it from remove the imaginary part from the denominator. And that's 3 minus 6i over 3 minus 6i. This is what it looks like. 5 plus 4i times 3 minus 6i all over 3 plus 6i times 3 minus 6i. And after you FOIL that, you're going to get 15 minus 30i plus 12i minus 24i squared all over 9 minus 18i plus 18i minus 36i squared. And because I squared equals negative 1, you can substitute that in. Multiply, add like terms. You can get 15 minus 18i plus 24, 9 plus 36, add like terms again. Get 39 minus 18i over 45. And the same thing, because they are both over 45, you can split them apart. It is the same exact thing. So you're going to have 39 over 45 plus negative 18 over 45 times I. And then it's going to be 13 over 15 plus negative 6 over 15i. And that's how you divide. And this has been 4.5 complex numbers.